Well, good afternoon. I'm going to show you how to solve University of Cincinnati's Science and Engineering College's multi-plane problem. And for the sake of time, I have already jumped in to where the free body diagrams have been drawn. And let me explain what I did. I start these problems off always by drawing a free body diagram first. So what that means, and here, I'll put it here step by step. Number one, draw the free body diagrams. Essentially what we're looking at is we start over here at M1 and we see that the downward vector is gravity, the upward vector is tension, but they're not even, okay? Gravity is bigger than this tension here. So how do I know that though? Well, look, if I read this problem and it says that these masses are connected by a light spring and it shows that the surfaces have a coefficient of friction and all the masses accelerate in the direction this way. So here's what we're going to do. We're going to say that this direction here is a negative acceleration vector. And we're going to say that this direction here is a negative acceleration vector. And we're going to say this going up is a negative acceleration vector. Math. How can you say that they are all negative? Because if these are negative, why is that negative? Well, because these are coplanar motion problems. Coplanar motion problems. Here, I'll write that down a little better. These are coplanar motion problems. So now that we've landed on orientation, and we know that everything is accelerating to the left or down, I know that the red M1G vector has to be bigger than the T1 to make that happen. So, if there's tension in the rope on M1, that tension is going to be shared up on M2. Because that's Newton's third law. That's an opposite and equal reaction. So the T1 that is going up is acted against by the T1 that's going to the left. Now, I've done a little trick to help you solve these problems, and you don't have to color code. But everything that's red is acting in the same direction together, and everything that's blue is resisting in the opposite direction together. So I know that T1 red is equal to T1 blue, but I also know that there's a force of friction acting on M2, and there's also another force of tension due to the string right here. So this guy right here is a T2, and that tension 2 has its friend, tension 2 acting in the opposite direction. So let me review what I know about this problem so far. I know that M1 has a little tension going up and a larger gravity going down, causing it to accelerate. I know that M2 has a tension 1 pulling it to the left that's bigger than F of F, the friction, and the tension 2. If I look at M3, I now notice that something is going up the incline in this direction. We can call that a direction. We can call that the x-plane. We can reorient our directions to say that's x and to say that's x. And then this is a coplanar x right here, acting involved here. Let me erase all this so we don't start to get like mega confused about what's going on. Take a look at M3. I didn't draw the M3G right here. I didn't use a red or a blue because that force vector acting on M3 is not coplanar. It's acting perpendicular to the surface of the Earth. It's not even involved. That perpendicular to the surface of the Earth, the only reason it comes into play is because it builds things that we need to solve this problem. We know that there is a normal force that acts perpendicular to every surface. We know friction acts downward and it's blue. But there's a blue vector sitting here undone. And I want to tell you that this angle theta is the same angle as the apex angle that forms between the force vector of gravity and the y component of that force and the x component. Remember, I'm referencing this x. All right, Matthew, but we got to be more specific than that to solve this problem. Okay, we can be more specific than that to solve this problem. Let's do it in terms of mg. If this force vector is mg right here, I could probably arrange that. I could probably say this is mg. If this is mg right here, then this is the opposite wall to that. So that's mg sine theta. And then this would be mg cosine theta. And all we have to do to solve for that is literally say cosine theta equals adjacent, which is that little fy over the hypotenuse. And our fy becomes mg cosine theta. All right, that's our fy right there. There it is, mg cosine theta. Okay, this is great, Matthew. How do we solve this problem when there are three masses? Well, the next thing we have to do is we have to solve for net forces. I'm going to solve for F net 1. And F net 1 is pretty easy. It's T1, which is positive, minus M1G, because that's a negative vector. And that equals a negative M1A. If I do the net force for the second one, look, that T1 is a negative force. Okay, so it's negative T1 plus that T2, and then plus the force of friction, which I'm now going to do this, mu M2G. How did you get that? Simple. The force of friction equals mu F of n. And so mu F of n in this case, the normal force that I would have drawn on this is equal to mg. I get it. So we can say m2g, we can substitute it in. So I'm literally saying the force of friction here is this, and then I'm re-terming it, and I'm going to drop that term down here. Okay? So that's what I'm doing. Hard to show on a smartboard, but that's what I'm doing. Okay? All right, but what does that equal? Well, that equals the mass going the other way. How about F net 3? F net 3 is a little bit bigger. It has that T2, which is negative T2. And then it has, going in the opposite direction, this mg sine theta. Okay? And then we're going to add to it mu M3G cosine theta. What? What do you mean mg3 cosine theta? Well, and that equals negative M3A, negative M2A, negative M1A. So why does it equal this? What is this? That's this. The force of friction. Oh, sorry, that looks terrible. The force of friction equals mu F of n. But our f of n equals mg cosine theta. According to our free body diagram. So we substitute in mu mg3 cosine theta. All right, so now what do? With all of this, we make a master net force equation. And I'm going to make my master net force equation down here because I ran out of space. So we know that F total equals M total A. Okay, so let's write all our net forces together in one fell swoop. T1 minus M1 G minus T1 plus T2 plus mu M2 G plus minus T2. Sorry, I didn't see the minus. There's a minus there. Minus T2 plus M3G sine 40 degrees plus mu M3G cosine 40 degrees. Whoa! That's the net force equals M1 plus M2 plus M3, and then they're all going in that negative A direction. I'd like you to look at the algebra and realize that we can cross out these T's to make our equation a little bit kinder. And then if we are to rewrite this and solve it for A, we can isolate for A and say negative A equals M1 plus M2 plus M3, and those are all over our master equation, which is negative M1G plus mu M3G plus M3G sine 40 degrees plus mu M3G cosine 40 degrees. All right, that is a lot to process. You may have to rewind this. I hope I didn't make a little error anywhere. It looks good to me. But at the end of the day, I hope you could appreciate that this equation that I just did is a derivative that will answer this question. And it really just restates Newton's second law that any total net forces is going to equal anything that has a net mass. That ratio is going to equal the acceleration. All right. Thanks for tuning in. I hope this was helpful.